Okay, so thank you, Adam, for the introduction, and thank you for inviting me to speak here, and welcome to my talk. I'll talk about some recent work on multilingual guidance for unsupervised natural language processing. This is joint work with Shai Cohen, who is actually defending his thesis in 2 hours, Slav Petrov, and my advisor Noah Smith. So the goal of this work is to learn linguistic structure without any labeled data in a target language. So given this example sentence, Baltimore has a thriving music scene. The goal is to predict structures like part of speech tag sequences or dependency trees that relate heads to their syntactic modifiers. Now, what is multilingual unsupervised learning? I have classified this area into 2 broad lines of research. The first that uses parallel data to project information from one language to another or jointly learn things together in multiple languages. And the second is one that doesn't use any parallel data to induce information in a new language. Now, obviously, the second is harder. Now, furthermore, each of these can be divided into 2 research areas. The first being joint learning for multiple languages together using parallel data. And the second is assuming that there is some supervision in some source languages and using that trying to learn structure for a new target language. Similarly, for the no parallel data case, you can similarly divide the research area into 2 parts. And there has been a lot of work in this entire domain of multilingual unsupervised learning. So today I'll focus on the second and fourth type of research in this slide, assuming that there is supervision in some source languages, and with or without parallel data, our goal is to learn linguistic structure for a target language. Okay? So in the beginning, I'll focus on this part, which is the assumption of parallel data, and with that we want to find structures for a target language. Okay, so in this part of the talk I'll only focus on the task of part of speech tagging. We haven't done any work in this using these ideas for more advanced tasks like grammar induction. So again, part of speech tagging is this task of annotating each word of a sentence with a syntactically disambiguated part of speech tag. Now, there has been a lot of there is a lot of annotated data in terms of part of speech information for English, and there are very accurate English part of speech taggers, and that's actually true for many other languages. So for 20 odd languages for which we have collected annotated tree banks, we have trained supervised part of speech taggers, and their accuracies are pretty good, ranging in the mid-90s. However, there are lots of languages like the ones on the screen which are pretty major languages with little or no annotated data. Each of these have several million speakers. However, even though there is little or no annotated data for these languages, there is a lot of there are resources that are like composed of parallel data with resource-rich languages like English. Are not new to this work. It has been used previously in many other grammar induction or unsupervised part of speech tagging work, including ones that have been done here. But this is like we are going towards a standard of building a coarse part of speech tag set that can be used to set up benchmarks. Now, these are nothing but mappings from fine part-of-speech tags in a language. For example, in English, we have these fine noun categories in the Pentry bank, and we map them to a coarse noun category. And similarly, we do this for the pronominal categories. And this can hold for the Spanish tree bank also. So the description of the coarse part-of-speech tag set is there in this technical report that we wrote a few months back. So the good thing about the universal part-of-speech tag set is that if we take the translation of the English example sentence into, say, German, we can use the same tags to tag its words. Moreover, if you take a very syntactically divergent language like Bengali, you don't really need any extra syntactic tags to capture the part-of-speech syntax of this new language. So this just says that these more or less generalize across languages, and it is useful because we can transfer information from one language to another by means of this coarse tag sets.
What did you say it was about Bengali that makes that easy?
It doesn't make, like, you don't really need extra part-of-speech categories to capture the part-of-speech syntax. So 12 part-of-speech categories that we have can capture all the part-of-speech tags, the finer ones that are present in it.
What happened to the verb in the Bengali sentence?
It is not there, because you can say sentences without verbs. Okay? Okay. So before I go on to our exact techniques that we use for part-of-speech induction for new languages, I would review briefly the state of the art in unsupervised POS tagging. So this is an hidden Markov model, which is a very popular model for sequence labeling tasks, and especially for unsupervised learning. So X is an observation sequence, the word sequence in this sentence, and Y is the state sequence, which I refer to the question marks over here. And each of the question marks refers to one of the coarse part-of-speech tags. Okay? So an HMM is composed with transition multinomials and emission multinomials. Okay? So when we train an HMM with the EM algorithm, which is one of the basic training procedures, the average accuracy across these 8 languages is not very good. Now, these 8 languages are the languages with which we experiment. These are not really resource poor languages. There is existing supervised data, but these are just since they have annotated data, we use this to evaluate our methods. And this also is the intersection with the Europol dataset, which we use for parallel projection through parallel data. So coming back to the EM algorithm, it only gives us 67% accuracy, which is not really acceptable for a practical task. So very recently, Bob Kirkpatrick and his colleagues proposed this model where they replaced the emission multinomials with locally normalized log linear models, where they have this feature function that looks at suffix, prefix patterns, whether the word contains hyphens, capital letters, numbers, and so on. And they found that this really helps for the Pentry bank case for English when they train it with a direct gradient based method. So we sorry. Okay, so Bob Kirkpatrick, they found lots of improvement for English using this method over basic EM estimated HMMs. So we tried to corroborate this, and we tried to experiment with our 8 languages and found that across all the 8 languages there are significant improvements over just HMMs estimated with the EM algorithm. Okay, so this is a good unsupervised model, and we wanted to adopt this for further experiments. Yeah.
How do you evaluate the unsupervised model?
So the fully unsupervised models over here are evaluated using something called many-to-one accuracy, where the HMM states are mapped greedily to the best possible goal tags on the test data. So, and it's a very bad metric, but it puts the unsupervised models at an advantage when we compare with other.
When you're measuring the accuracy using this method? You're measuring it against the universal part-of-speech tags.
Yes, yes. So that's a great question, and that's why our numbers are pretty high. We will see very bad numbers in the second half of the talk. Okay, so we ran another Oracle experiment where we assumed that the possible set of part-of-speech tags for every word in our vocabulary is given. For example, the third word over here, ein, can associate with these 4 part-of-speech tags. And if that information is given, the HMM's state space is constrained because we already have this tag dictionary. Now, if we assume that for our languages we have these dictionaries, results are very good. So when we compare it with the feature HMM model, and we train the feature HMM with the dictionary given, and then test it on the test sets, we see numbers in the range of low 90s, which is extremely good in comparison to purely unsupervised models. So they are nearly close to supervised models. So this says that some sort of constraints in the form of dictionaries can help a purely unsupervised model. And this is the idea that we want to develop, and we want to use multilingual information to improve purely unsupervised models. That's what we are trying to, that's what is there in the following slides. Yeah.
So when you evaluate when using the Gold Dictionary, do you not allow the many to one?
Yeah, so everything with the dictionary over here, we don't have many to one. It's just using the dictionary tags. Okay. The prior distribution over tags, we don't use that. We did.
You did. I assume the transition probability will be giving regular additional.
Sure, yes. We actually tried to incorporate that sort of information as features in the feature-based HMM. Somehow it didn't work very well. But that's a possibility to explore, definitely. Okay, so for most languages, access to, yeah.
What do you get if you just use the first definition in the dictionary every time?
More than 90% actually.
Right.
Yeah.
So how much better are you than that?
3% better than that, maybe.
At that much?
Yeah. So it's part-of-speech tagging is a really easy task.
Well, I understand.
But
I'm wondering if the baseline is. I wonder if you're at 3% above baseline.
yes, yes, yes.
Well, the other way to think about it is that the error rate is 10% and he brought it down to 6.
No, I understand. I suspect the baseline's even higher.
Yeah. The most frequent tag baseline is around 91%, I think. So, so for most languages, access to a tag dictionary is not realistic. So this is especially true for morphologically rich languages, which only have base forms in dictionaries. So our idea is to use supervision in resource-rich languages, then use parallel data, and then construct projected noisy lexicons which we can use to constrain the feature HMM. Okay. So next we come to the idea of bilingual projection. So given this English sentence, we already have a supervised part-of-speech tagger from which we can gather automatic labels with very high accuracy. Now, let's say we are trying to build a tagger for German. We can take this sentence's German translation, and we can also gather automatic unsupervised word alignments from translation data, and this is available for a variety of languages. Now, a direct projection model, which has been explored before, can just project these tags across the alignments. There will be some unaligned words, and you can do something reasonable like assuming it has the noun tag. And once you do this sort of direct projection, you can gather more projected sentences from your parallel corpus, and then perform supervised training to get a supervised tagger. Okay? And when we did that for our set of languages, this resulted in even better accuracies than the feature HMM model, which says that projection can give you, like on an average, it gave us nearly 6% improvement over a unsupervised baseline. Yeah.
The direct projection line used in ordinary HMM or feature HMM?
No, this is not. This is actually the TNT tagger. which is a trigram HMM. It has more tricks in it. So we just trained it. It's more powerful than a bigram HMM or a feature HMM, I think.
Okay, fine, but you could take TNT and add features. I mean, I'm thinking for morphologically rich languages.
Yeah.
Getting some projection might give you quickly a signal that certain endings were reliably signals.
Right. So I also trained a supervised feature HMM on these languages using the projected data, which I'm not presenting. They are sort of like these numbers. I mean, we can examine more interesting trends there, but those were not very interesting, so I didn't put them here. But you can.
So you're saying that the benefit of using trigrams is about the same as the benefit of using features, but you haven't tried using both of those?
Yeah, we haven't. Yeah.
One more question.
Yeah.
So the direct projection is trained off of the 50 million words of the parallel text in the Euro file?
No. Actually, it turns out that this is only trained on as many number of sentences as there are in their tree bank data sets. So this is a controlled experiment, but we also trained it on that many million sentences, and results are worse than this because there is more noise, I think. So, okay. Now the next idea that we consider is projection at the level of types instead of tokens. So far we were looking at direct projection at the level of tokens. So at the level of types, what you can do is again take such word alignments with the English side tagged with an automatic tagger. And this idea is not new here, it has been explored before. So what you can do is throw away the sequence information. There will be unaligned words, ignore them, and take this bag of alignments. Now, in the next step, you can project softly the distribution over tags for the English side to your target language side. So over here, each of them, like only one tag so far has got all the weight. As and when you encounter more parallel data with the English words tagged, you can update the projected distributions. So you can do this for all your parallel data, and at the end, you will have a collection of distributions over tags for each token that you found aligned in your parallel corpus. Okay? And this is basically the probability of a tag given a word. You can threshold this probability with some threshold tau and construct dictionaries for individual words. Okay? And when you do that, and we constrained our feature HMM with such projected dictionaries, turns out that you get improvements for 6 out of 8 languages, which is encouraging, saying that type level projection is better than doing direct projection across just tokens. So our final idea is an improvement over this type level projection idea, which is basically there are unaligned words about which you don't know anything, and the question is whether coverage can be improved. So the way we do this is by expanding the projected lexicon using semi-supervised learning. Okay? Like not really semi-supervised learning, but weakly supervised learning. Yeah.
So what is the difference between number 1 and number 2?
So in number 1, you are just projecting the tags across alignments for one sentence, right? For the second sentence, you again project the tag, and you do this for all the n sentences that you have. So you have a noisily tagged projected data set, which you just use to train a supervised part of speech tagger. That was idea number 1. Idea number 2 is you collect the distribution over tags for each token in your target language, construct a dictionary.
Number 1, the super was training manually,
Right.
super was training number 2 with dictionary.
Exactly.
I'm surprised that it comes out differently since over the entire corpus you get that same distribution when you're just projecting one best tag.
That's a great question. So we also were wondering about the same thing. It happens that the thresholding removes a lot of noise. Yes. Yes. So this was a paper from 2001. Yep. So our idea is to use label propagation, which is
Maybe ask you one more variation on this, and I think it will just be a minor variation.
Yeah.
So when you do the supervised version after projection,
yeah,
you freeze those tags forever and ever.
exactly, yeah.
What if you retag the data after one iteration?
Yeah, it may.
Your training data.
Yeah, it may improve. I don't know. It's somewhat like self-training then, basically.
Yes, because I have a feeling that normally self-training doesn't do you a whole lot of good.
Right.
If you start with noisy data but enough that you get a decent first model.
Right.
For example, the effect of thresholding and all that you do with your distribution,
Yeah.
you might get that for free.
Right. Possible. Or you can impose constraints while labeling your unlabeled data in the form of thresholding, maybe. And that's actually a research area that lots of people are exploring. For example, in Dan Roth's group, they do constraint self-training. Basically, it's a similar idea, I think. Yeah. Great question. We just chose a random threshold and it worked. Yeah. So I have some work where choosing the threshold is not necessary, which I'm not going to present here, but that's the biggest weakness of this work. Yeah, choosing the threshold, because it's an unsupervised learning task. Okay, so how can label propagation help? So what we did was we take a language and build a graph over 2 million trigram types as vertices. Now, we choose trigrams because trigrams, so we are only concerned about the middle word of the trigram, and we are trying to induce distribution of our part of speech tags for the middle word of the trigram. And we choose trigrams because the left and the right context of a particular word disambiguates a lot and gives you only 1 or 2 possible tags that the middle word can take. Okay, and it also helps us create a nicer graph than creating a graph over only words. So we are, again, as I mentioned, we are interested in the tag distribution over the trigram's middle word, and that is the label distribution at each vertex for graph-based semi-supervised learning. And this representation was actually chosen by these guys who, Subramania, Petrov, and Pereira, who worked on POS domain adaptation for adapting a Wall Street Journal tagger to, say, the bio domain. Okay, so basically this is an excerpt from the German graph, and if you can read German, you'll realize that the top and bottom right section of the graph is syntactically disambiguated automatically via the graph construction process. So the edges in the graph come from distributional similarity, and automatically you get some sort of syntactic disambiguation. Okay, so what we do next is that, since this is not an ideal semi-supervised learning setup, to seed the graph we need some sort of information, and that comes from our source language. So we plug in automatically tagged words from a source language like English, and the links between the source and the target language units are just word alignments. So when we do this, it looks like this. Basically, say the SN word over here was aligned to food, eating, eat, and eat, and each of them were automatically tagged in context by a supervised tagger. Similarly, there are other words, and I call these vertices the vertices at the periphery of our target language graph. Okay, so we run first, in the beginning we run one stage of label propagation where information is transferred from the source language to the target language, and this is done by just propagating softly the distribution over tags to which one particular target language unit is aligned to, the proportion of things that it is aligned to. So over here SN is aligned to noun only 1 out of 4 cases. So that's how you project the distributions. So this is, yeah.
Sorry, one more quick clarification question. So here you're only showing a single English word, but you're actually choosing that English word based on the n-gram in the German, right? So it's not...
Right, that's right. So this trigram actually had this alignment form in the parallel data. Right. So,
And one more detailed clarification. So when you say that fine adjective, good adjective, nicely adverb are all aligned to this is good day, whatever the diagram is, you're saying that they're aligned to that trigram, not just to the word too.
They are, yeah, they are aligned to the trigram, yes.
Well, they're aligned to that. They're tokens, right? So the things in blue are tokens.
The things in blue are tokens, yes. But you can imagine them to be types with distribution over tags. The same thing. So, so after doing this seeding procedure, we run the second stage of label propagation, which is traditional label propagation within the target language vertices, and we use a graph objective function with the quadratic criterion. And the way it works is just propagates the seed distributions throughout the graph and runs until convergence. So at the end, we get larger set of distributions, and we create a larger dictionary by using the same thresholding mechanism. So this shows the green bars over here. They show that we get many more thousands of words in our projected dictionaries once we used our graph-based technique to expand the lexicon. Okay, and although noisy, we hope that this will give us better results. So a 2-slide overview of what we are doing actually in terms of label propagation. So in semi-supervised learning using graphs, there are data points. Some of them are labeled and most of them are unlabeled. And there is the geometry of the data given in terms of a symmetric weight matrix that connects pairs of vertices with non-negative weights. And there are supervised label distributions over here, Q1 and Q5, and the goal is to learn Q2, Q3, and Q4, which are the distributions over unlabeled vertices. And we use this objective function proposed by Jerry Zhu and others, where we are trying to optimize this objective function over the set of distributions over the unlabeled vertices, and there are two big terms over here. In the summation, we have all the unlabeled vertices, and we iterate over all its neighbors and try to minimize the distance between their distributions. So it's a quadratic or a Gaussian field, if you will. And the last term is basically like a unary penalty, or you can think of it as a regularizer that brings the distributions of uncertain neighborhoods close to the uniform distribution. This is like a maximum entropy term over here. So once you minimize this, there are iterative updates for optimization, and you get the best set of distributions. You do map inference to get the best set of distributions over unlabeled vertices. So final results using our expanded dictionary, they are very good.
One quick question.
Yeah.
Did you set that lambda parameter randomly?
No, those were just random. Like, yeah, so the lambda parameter was extremely low, like 0.0001. The other one was 0.1, and those were not touched. Those were just kept there. Usually in semi-supervised learning, people tune them on some label data. So we get improvements for 7 out of 10 languages over all the projected and unsupervised baselines, and these are all statistically significant. The average improvement over the feature HMM baseline is more than 10%. For German, we didn't get improvement over the direct projection model. That's only the outlier. Yeah. Yeah.
So in this case, like when you say difference between Q and Qj, you're constraining it to be these are densities, right? Probability.
Yes.
So did you try some other distance metrics?
Sure, that's a great question. So not in this, yeah.
Could you repeat the question?
Oh, this was he's saying whether we replace the Gaussian field with some other field with a more interesting divergence metric. So that's the question, right? So yeah, so there have been lots of work on this area. We have done some work, but not in this setup. This can be replaced with things like, say, the KL divergence or the Jensen-Shannon divergence. And actually that last penalty is also very strange. It tries to bring things to the uniform distribution. You can replace it with more interesting penalties. But we haven't explored that in this work. Okay, so to put in perspective our best results with the gold dictionary results and the supervised results, we are still far away from those numbers, but we are bridging the gap between unsupervised and purely supervised methods by a lot. Okay. So in summary, reasonably good POS taggers without direct supervisions, and we have evaluated on 8 major European languages that have annotated data, and we are going towards the standard of universal POS tags, and these part-of-speech tag sets actually have been used in many more research projects recently. And so again, unsupervised part-of-speech taggers are evaluated using metrics like many-to-one accuracy and one-to-one accuracy, which are controversial metrics, and we avoid those by using the projection mechanism that we have. Okay? So back to our, any questions so far?
I have
Yeah.
a question to contextualize your results. So for an accuracy of 83, you said you use unsupervised or semi-supervised or projected, I guess, methods. Like how much label training data would you need in order to reach that level?
Very few. Maybe 100 sentences. So so that's a good critique of this work, but turns out that just getting 100 labeled sentences, say in Malagasy, is difficult. So we have used this for parsing and for POS tagging Malagasy sentences, which are being used for machine translation. Okay, yeah.
Also, all of the unsupervised methods work worse than that dictionary baseline, right? That just says just pick the first definition.
Yes, true.
Yeah, and in your slides, it looked like there's a difference between Romance and Germanic languages. That the unsupervised methods are working better in Romance than in Germanic.
Right, so we have German here, and what is the other? Dutch.
Well, German, Dutch, Swedish,
Yeah.
Danish.
That's right.
I'm saying put them on one side,
Right.
everything else on the other side. And the difference is that in Germanic you would really see much more morphology and
Sure.
word order is less important.
Right.
And since you're using word order, you would expect that it would be better in that.
Right. So one extension of this work can be where you want to, you have a target language and you choose a source language which is similar in terms of their,
English is pivot, it's got both.
yeah, but if you want to induce, say, things in Dutch and you have German data, that may be, yeah.
But you see, I think all your unsupervised methods are largely about word order, and that's really much better in Romance than in Germanic.
Right.
So I just wouldn't expect it to work both.
Okay.
Yes.
Okay. Yeah.
So once you have the 83% accuracy results, say you give those to a human, would that significantly reduce the effort needed to tag purpose?
That's
Or would you be able to do a pretty good job given an 83%?
Great question. I don't know. That may be a study by itself.
So as a follow-up, what's the distribution of errors?
I can't tell you right now, but we saw that when we were evaluating it, but I can't tell you right now.
It would be interesting to know whether the errors are systematic, among other things. So you could think a lot of things about errors. You know, errors might be on rare words, or errors might be on
Right.
But one of the big questions is whether errors are systematic. So if you took this as the initialization for a supervised TBL tagger, would you be able to fix up? So you can think about the many-to-one mapping that you're doing as being the first thing that a TBL tagger might be.
Yeah.
So you're in one vocabulary, and it would be switching to the universal vocabulary.
Sure. So I'll give you an interesting result, which we don't have in the slides. So we took the projected tagger, and we trained TNT with the projected tags. We get 2 or 3% better results than what we have here. So it's somewhat like the first step of doing TBL, maybe.
Thanks.
Yeah. Okay.
So 2 or 3% better than the 78.8.
No, 2 or 3% than 83.4. Yeah, but I didn't say that it's a hack basically. So that's why anyway, I think I should go to the next part because that's like 15 to 20 minutes more. Okay, so this is the hierarchy, and this is technically more interesting than what we saw so far. Basically the setup where we don't have no parallel data and we have supervision in source languages. We're trying to induce structure for target language. Okay, so this is the setup. We have annotated data in some helper languages, for example Spanish and Italian over here, and the unlabeled data is in our target language, for example Portuguese. And the end product that we want is the set of Portuguese parameters for a particular task. Okay, so what we do over here is we estimate coarse universal or coarse parameters for the helper languages, and assume that for our target language its parameters are nothing but the interpolation of the coarse parameters in the helper languages. Okay, and the interpolation weights are learned automatically using unsupervised learning. Okay, so once you have the interpolated parameters, these are coarse ones, so we use those to initialize monolingual unsupervised training in the target language in terms of its fine syntactic categories, and that gives us the final parameters. So this is the roadmap. Okay, so we will go into the details of these. So the first assumption that it can be any task, we have tested it on 2 problems. The assumption is that the underlying model is generative. So for example an HMM like we saw before, or the dependency model with valence, which is a popular model for grammar induction. Okay, so we know that they are composed of multinomial distributions, these models. For example, for HMMs the transition probabilities are there, which we call theta. So remember that so there are 2 types of parameters in these models. The unlexicalized parameters that doesn't look at the surface words, and then there are the lexical parameters eta, which look at the words. So these are the transition probabilities in the HMM. So remember that theta denote unlexicalized parameters and eta denote lexicalized parameters. Similarly, for the DMV model there are parameters like the probability of a child given its parent on the left direction. So this is the DMV model contains only unlexicalized parameters because it is defined over part of speech tags usually. So we call them theta sub C generated from P. Okay, so theta and eta are the 2 types of parameters in these models. So in general unlexicalized parameters look like theta k comma I, where k is the kth multinomial in the model and I is the ith event in the multinomial, where for example it can be the transition probability from an adjective tag which is k and to the noun tag which is I. Okay, so the lexicalized parameters eta take a similar form. There are no lexicalized parameters for the DMV model. So in general the probability, the joint probability of the sentence and some sort of derivation is the product of all these probabilities, each of which are raised to the number of times the event I of multinomial k fires in the derivation. Okay, this is straightforward. So the second assumption is what we had before in the first part of the talk also. Coarse universal part of speech tags are there. These are those 12 ones that I mentioned before. And for each language L there is a mapping from its tree bank tag set to this coarse part of speech tag, and this is there for the helper languages, or if you have a target language for which you know the part of speech tag, you have this mapping. Otherwise you can construct a random mapping. Okay, so the next thing is that for each helper language in our set of L helper languages we have a tree bank, and we have converted it to a coarse version using the fine to coarse mapping that we have. Okay, and finally we use maximum likelihood estimation to estimate the unlexicalized parameters theta superscript L for that particular helper language. Okay, so these are the three things that we know that are there. So this is the crux of this part, which is multilingual modeling. Basically, for a target language, we define its unlexicalized parameters to be the interpolation of the corresponding unlexicalized parameters in the source languages. So this is the interpolation step. Over here, theta k, bold theta sub k, is the kth multinomial in the model. Maybe say the transitions from the adjective tag in an HMM. Okay, and over here, beta sub L comma k is the mixture weight for the kth multinomial for the Lth helper language. Now what is interesting is that these beta Lk parameters, they sum up to 1 if you sum over all the languages. For given k, they sum up to 1 for all the languages. So they lie in a probability simplex. Okay, cool. So for our two, these are some examples for our two helper languages, Spanish and Italian. Let's say we learn them. So I'm coming to that. So theta adjective for a particular language, say, is the interpolation of beta Spanish comma adjective and the corresponding multinomial distribution in Spanish plus the Italian counterpart. Okay, so let's say the theta adjective in Spanish and Italian look like these. These are probability distributions, and the betas are 0.7 and 0.3, which sum up to 1. So we can get our new theta adjective, which is, we assume it is the probability distribution for the transition from adjective for our target language. So this is the interpolation step. Now unfortunately, these two are unknown, and we learn them. Okay. Now how can we perform learning in this setup? It is straightforward. In general, for normal learning, we try to maximize the marginal log likelihood of the data, and here the probability of the sentence and the derivation is this product of all the parameters that we saw before. And in case of multilingual learning, it is the same, except that now we optimize over beta and eta. Okay, the lexicalized parameters stay the same. Beta are the mixture weights. Now going into the detail of this, each theta ki is actually replaced by this mixture of the helper parameters. And note that the helper language thetas are fixed, so the only things that you learn over here are the beta parameters along with the lexicalized parameters eta, which are unchanged. Any questions about this step? Okay. So learning beta with EM is easy. So basically you just run the EM algorithm and use the expected counts. So over here, G sub LK is the number of times the corresponding beta is used in a derivation, and then you sum up over all the derivations that you have, and you get the expected count of the number of times beta LK has been used. And in the M step, you just normalize to get a new beta in the next step. So we can learn betas using the EM algorithm. Moreover, how about feature-rich generative models which replace multinomials with log-linear models? Our model can be easily extended to these type of models also, because we can use the same expected counts and use the chain rule to get derivatives of these mixture parameters. Okay, and I don't want to go into the details of how we compute the derivatives. So both vanilla unsupervised models, which is basically a Bayesian network and has multinomial distributions as parameters, as well as models which have locally normalized log-linear models, both can be estimated easily using our techniques. So finally, when we learn these betas, we can use them to construct our coarse set of parameters for a target language. Now once this coarse set of parameters are there, what we do next is we do a coarse to fine expansion by first copying the parameters exactly for all the fine tags that appear in the k position of the multinomial. So for English, say the adjective tag expands as 3 types of adjectives. We make identical copies of this transition distribution, and for each we just take them and expand. Sorry, this eta is a bad animation. So the nouns are then, for example, expanded to 4 fine noun categories for English, and this is done for all the tags that appear in the column vector that we have here. So this will give us an expansion of the learned parameters in terms of the fine parameters for a particular language, which are then used for monolingual unsupervised training in that language in terms of the fine parameters, which will eventually give the final parameters that we wanted to learn.
Sorry, what breaks the symmetry of the unsupervised training?
So in terms of the log linear model that we have for part of speech tagging, we just do random initializations for many runs.
Okay, so singular and plural noun phrase might come out backwards. What you're saying is you don't initialize exactly to 0.065. It's 0.065 plus some epsilon.
No, actually, just 0.065. I tried breaking symmetry. It gave very bad results somehow.
Then I'm still confused. I'm sorry. So the reason that you want to go from coarse to fine is so that the different types of noun can specialize?
No, I want to go coarse to fine because eventually I want to measure accuracy in terms of the fine part of speech tags.
Sorry, Jude.
No, I thought that's what you.
So, yeah, how do you know which words go to NN and which ones go to NNS?
So they are
arbitrarily assign all the symbols.
So the HMM states so we initialize these, say we have 45 tags over here and there are 45 HMM states. So we just choose state 1 to represent NN and state 2 to represent NNS and so on. And at the end, when you have finished training, you just use 1-to-1 accuracy, which is a greedy metric to evaluate.
So you don't know which are which, and you're going to just evaluate.
At the end, if you,
But I'm still confused about what you said. How you don't do symmetry breaking? So
Yes.
Why don't NN and NNS have exactly the same parameters?
Yes, that's a great question. So I don't know why it happens. I tried both versions. One where I used like equal division, and the one where I add an epsilon. The epsilon case performs much worse. And this was reflected in the grammar induction experiments also.
Okay. Well, you said a look of confusion on my face, but maybe you should call.
Yeah, we can take this offline about
The thing is basically when you spread it equally, you try to do the EM algorithm, they are going to get it's not going to change, right?
it will change because the lexicalized parameters are being trained from scratch, right? So there are 2 types of, this is only happening for the unlexicalized parameters. So the lexicalized parameters start from some random point.
Oh, so you do break symmetry there.
We do break. That's yeah. Okay. So So experiments, 2 problems: unsupervised part of speech tagging and grammar induction. So we have 10 target languages, lots of intersection with the previous part of this talk. Bulgarian, Danish, Dutch, Greek, Japanese, Portuguese, Slovene, Spanish, Swedish and Turkish are our target languages, and we use English, German, Italian and Czech as helper languages because they belong to diverse language families and also have a lot of annotated data in the kernel tree banks. So I will not give you detailed numbers because there are lots of numbers. Instead, I will say we have 3 models over here. I will say the number of languages with best results for each model will be tabulated here, and also the average accuracy. So the first baseline we consider is just the monolingual baseline of Burke-Kirkpatrick. The second is uniform mixture parameters, where we don't learn the betas at all. So just take uniform betas and do interpolation, and then we learn the mixture. And in every case, we do coarse to fine expansion and then initialize and do EM again. So for 6 out of 10 languages, we get best results with our model, but the average is dismal because we use 1-to-1 accuracy, which gives you worse numbers in general, and also we evaluate on the fine part-of-speech tag categories. Yeah.
What would happen if you inserted a column just before the last one, which is a model where the betas aren't uniform, but they are tied across all the multinomials? So you say English is always, or I'm sorry, Japanese is always a 2/3 interpolation from English to Czech, and it's that for all the multinomials rather than learning, okay, it's 2/3 for nouns.
That's a great point.
1/3 for verbs.
That can be a model. Yes, we haven't tried that. Yeah.
I mean, I'm just, the betas for that model might be interesting to look at.
Yeah. I have some.
About which languages are related.
I have some slides that shows the betas and how they look like. Yeah.
So if I understand, the reason that it's better is because, I mean, the ultimate model is the same, but it starts in a better place because you use this as initialization.
Exactly. Yeah.
So do you restart from different initialization points?
No.
So that might itself be 46.
So I had like 500-600 experiments to run just for this problem, but definitely. So we also had a discussion about interpolating the lexicalized parameters. That will be really interesting, especially for part-of-speech tagging. Okay, so in terms of dependency parsing, results are much better. So we have 3 strong baselines: the EM, monolingual EM baseline from Klein and Manning. We have posterior regularization, which is a weakly supervised method, and phylogenetic grammar induction that tries to do grammar induction together for a phylogenetic tree. And we have 4 versions of our model. The first one is uniform mixture parameters, but no coarse to fine expansion and relearning. So the good thing about grammar induction is that we just want dependency arcs. So there is no necessity of doing at the level of coarse or fine. Like there is no you cannot like doing it at the level of fine tags is not essential. The second model is similarly learned mixture parameters, but no coarse to fine expansion. And these are the 2 counterparts where we do coarse to fine expansion and monolingual learning as a second step. So here are the numbers for the baseline. Posterior regularization performs best for 2 out of 10 languages, but the average for these baselines are very low, like in the 50s at best. Our models do much better. The best results are in the low 60s, and in terms of number of languages with best results, the things are mixed. They are distributed strangely among our 4 versions of the model. Now, although our mixture model where we learn betas is the best, it is not much better than the model that uses uniform betas. So that's discouraging, but it also shows us that just using these interpolation weights blindly without any sort of tying parameters is not a great thing. So that paves a way for future research. But overall, the take-home message is that interpolation of this form can be useful to develop fast, like in a very swift way. If you want to build prototype dependency parsers, you can use this method. So basically, we analyze beta using principal component analysis. So beta is quite high dimensional. We bring it to 2 dimensions, and we see that related languages have similar betas, like Portuguese and Spanish, Dutch and Danish, Bulgarian and Slovene. But this is a very hacky way of visualizing things, and we should not take it very seriously. But this is interesting from the point of view of finding similar languages or completely dissimilar languages further away from the cluster.
So you didn't plot the helper languages, but you could have, right? It's 1000 interpolation.
Yeah, we did not. Yeah. Okay. So the final result, I'll go over it really fast because it's 55 minutes. So in the final experiment, what we did was we tried to do grammar induction directly from words. So we get the part of speech induction model and the grammar induction model interact by using a sausage lattice. Basically, we get the posterior distribution of our part-of-speech tags at one position for a sentence, and we jointly try to decode the best dependency tree by parsing this lattice. And this gives us really interesting results. Basically, as when we do this lattice step, we get a dependency parsing accuracy of nearly 58%, which is only a few percentage points below the best average result with gold tags. And the pipeline model that doesn't use this joint decoding step is much worse than the step where we trying to do joint decoding for part-of-speech induction and grammar induction. Okay. So finally, in summary, improvements for the two major tasks using non-parallel guidance from source languages. In general, grammar induction results are better than part-of-speech tagging because we have some intuition why this happens. It is because syntactic dependencies transfer much better than, say, transition probabilities for part-of-speech tagging. And at the end, we tried this experiment for joint POS and dependency parsing, which performs surprisingly well. And for a few languages, results are even better than using gold tags. Okay, so here is the conclusion. So we have seen that leveraging weak supervision from resource-rich annotated languages can result in good improvements in unsupervised learning for various tasks. And projection with parallel data results in a better performance score usually. And extensions with like more than one source helper languages are possible. And the final point is that rapid development of NLP tools is possible for new languages, and this is in fact being done at Google, where the first part of the work was done, and also in a resource poor MT scenario at CMU. Okay, thank you. Yeah.
So did you specifically choose what helper language to use for? But you could have said, what if you had thrown in all whatever?
Sure, sure.
It should have learned the right.
Yes, definitely. So initially we were trying to choose one helper language per target language, and then because of time pressure, because we couldn't do that, it was just before the paper deadline, but definitely. So there was another paper at EMLP where that was exactly what was done, but with parallel data, where they had Oracle results with the best possible source language and also with all the source language from where they are learning for a target language. That is possible, yeah.
And was it better with having all of the languages?
For their case, yes, yeah.
So harking back to the first half of your talk, I'm a little bit surprised that the projection didn't work better. So do you have any hypothesis as to why? I mean, is it that the tags is it that the English tagger is bad when it's tagging the English, or is it the word alignments are bad so that the projected tags are bad?
So
there's a mismatch between the parts of speech on the English words and the correctly aligned German words.
Right.
Do you do any sort of error analysis?
So the word alignments that we used was the same for all the three projection models, and the alignments that I chose were the extremely high confident alignments after symmetrization. So I don't know what exactly they were using, but it was from Google's translation engine. And since I chose the high precision ones, I threw out a lot of alignments. So it may happen that many of the target side tokens were completely unaligned. So that's a space that can be explored further.
So that would have negative effects for your direct projection.
Yes.
If your fallback strategy for unaligned words is the majority tag.
Yes.
But it seems like that wouldn't have that as big an impact for your distribution dictionary.
Not sure about that. That can only be validated by an empirical study, I think. because the tag dictionary, if it is, yeah, David has.
One way to reframe that is, if you have gold standard using the English lines, how often are the core speech tags different? Exactly.
Yeah, I'm not sure of that number. Do you have done? Have you done studies?
That was basically divergence. You often will have a normalization not to a verb and vice versa.
Right.
Or many new ones. It's hard to figure out which one is the proper like.
Adjectives in one language could be nouns in another. It seems to me like you should be modeling what the confusion matrix looks like between a given pair of languages.
Right.
And that would be shared across everything in your graph. So
Mhm.
you can just learn, okay, it's okay if this is an adjective
Sure.
in English and in nine lines to part of a compound noun.
Right. So there is a scope of imposing interesting unary penalties in the graph-based learning technique, where you have regularizers that tie together certain part of speech tags, maybe.
What I had in mind was actually more binary, I think, that you recognize that this part of speech in this language often goes with that part of speech in that language.
Okay.
So, right now your notion of comparing two distributions is homogeneous.
Yeah, but so that can be incorporated as a prior knowledge thing, right? Because you're seeding.
Or you could try to learn it. You might not be convex anymore, is the danger.
Yeah.
I mean, would you start with small amount of tag data on the target side, or you would just learn it all, like learn these speech tag changes just totally unsupervised?
Well, of course, it's always nice to have some data.
Yeah, but I mean, maybe you wouldn't need as much data to learn that nouns often change tags.
That might be, well, if you have some gold standard, as David said, you might just be able to pick this up quickly if it's a line.
If there is some gold standard, unsupervised POS tagging is not very useful, I think. If there is very little annotated data, you can already have a very good part of speech tagger.
You also can address this in your evaluation cost point, because if you have silk shirt and in some four language it's silky, it's adjectival there, and you project the adjectival label. Labeling a silk shirt as an adjective is not that's a low cost mismatch, while other things are much higher cost.
Sure. Mm-hmm.
That's one of the major reasons why you have the threshold and applications, because you look at lots of noise.
Yeah.
So I'm concerned going back to Chris's thing about alignments and how this might play off between Germanic and Romance. So consider Spanish, English, and German. They all use about the same number of characters to express the same concepts. But Spanish uses more spaces than English, and German uses fewer.
Okay.
So when we're doing these alignments, if you define a word in terms of white space,
Right.
then I would think that German would have the fewest number of words, and Spanish would have the most number of words, and English would be somewhere in between. When I'm aligning these things, I would think that a lot of the German words would correspond to two English words.
Right.
Whereas, Spanish, you have multiple words corresponding. So I would end up with a lot of unaligned English words or something, right? When I'm doing these alignments, right? Or some, I'm just worried about what happens if I have a lot of, it seemed like you had some examples where the unaligned words were problematic.
Yes.
To show that the errors are sort of left, the remainders, the old maids are sort of getting stuck with more error, and that would cause that these alignment problems sort of almost necessarily end up with more old maids in some language.
Yeah, so the last model where we expanded the lexicon projection model via alignments tries to address that problem, because for the unaligned words, we're trying to induce tag distributions using this semi-supervised learning technique. So you can think of obviating the problem of alignment by just propagating information across similar types. That's the graph-based thing trying to do.
Right, but I wonder if even against your attempt, the question is, does it succeed? Does it turn out that sort of the unaligned words have a higher error rate than the aligned words?
Right. That's an analysis I should do. Yeah.
In fact, in general, in this whole part of speech induction tagging business, since you have these results that show that if you use the most frequent tag or even the first tag in the dictionary or in the dictionary distribution, you do so well. perhaps what you should do is take your test set and eliminate from consideration any token that has a unique part speech tag.
Right.
I'll only worry about if I got the rest of them right.
Right,
So
right,
you may
right.
have to take a test set that's an order of magnitude more,
Sure.
but your evaluations then will be more meaningful.
Right, right, right.
Because after all, like, Baltimore, I don't need to look part speech tag.
Right, right, right.
Most probably not going to be able to now.
Right.
Especially in your course categories in the first part.
Right. True.
So I would think that that might actually help you focus on these problems and answer some of these questions.
I'm confused. Why don't you need to know Baltimore's part speech?
No, I mean, for example, if you had 100 sentences tagged in this new language, and then you could identify that these are the words that have pretty stable parts of speech, maybe a few hundred sentences, then you would say, okay, let's use that as dictionary supervision. And for the remaining words, you just keep it open. And so the real learning issue has to do with which words, what is the information that you're missing? Because this unsupervised learning, it's learning a lot of stuff that's good, but it's also learning a lot of junk. And if some simple supervision could get rid of the junk, then you would want to do that. So learning on things you don't know. And the evaluation I mentioned is just a proxy for that, saying let's ignore errors, assuming that some supervision will fix them.
So he's saying that to evaluate, don't consider the words which are not ambiguous.
Right, but at the time that you're doing unsupervised learning, you don't know that they're not ambiguous.
No, this is just during evaluation.
In a morphologically plural language, most words probably only have one part of speech.
Right.
And those are the rare words, or those include the rare words, and those are ones where you're going to have trouble because of the size of the lexicon in doing further processing.
Yes.
Back off to part of speech.
Right.
So why wouldn't you want to know that Baltimore is an M?
Or maybe you want to just threshold to things which appear frequently enough for a speech tag them, like the 1,000 most frequent words in the language of those that are unique. What I'm saying is that a lot of the analysis of what's going on, what's still left to be done, is clouded by the fact that the learning problem is very asymmetric, because a very little supervision fixes a big chunk of things, and the action is all on a few things. And those few things might be in the category of these things are variable, they have multiple tags depending on context, or it could be that these things are rare, so you're not going to discover their tags in the limited amount of data. And I'm saying somehow unsupervised learning should focus on that and not cloud the evaluation.
So I think in summary what the graph-based approach is doing is just expanding your lexicon in a probabilistic way, and then using that knowledge to constrain a structure prediction model. And that is just expanding your vocabulary. So in Jason's example, for example, for a morphologically poor language, this will do really well because it will get possible distributions over tags over the rare words that you don't see. Any more questions?
Thank you again.
Thank you.